um, Immaculate, the late Immaculate. So we have the collision of molecules and atoms. Okay, collision of molecules and atoms. Okay, against the container or against themselves. So the collision of atoms or molecules within a container, okay, is an example of perfectly elastic collision. Practically, when we come to our various applications, elastic collision applies to bodies that are hard and bouncy. So you can, in real life experience, elastic collision is seen in bodies, is observed in bodies that are hard and bouncy. They can bounce. So example, if a football is kicked, it's kicking off a soccer ball or a football demonstrates an elastic collision. Applying or hitting a tennis ball with a bat or table tennis ball with a bat demonstrates elastic collision. And then the snooker ball, okay, hitting the snooker ball with the stick for it to hit another ball also demonstrates elastic collision. In all these examples, please be putting down examples yourself. So as I mentioned, so when a bat, okay, is used to hit a tennis ball, snooker ball, or billiard ball, they all demonstrate elastic collision. Why do they demonstrate elastic collision? It is because, look at the tennis ball. When I hit, okay, the tennis ball to the floor, when I move it to hit the floor, the tennis ball can rise to the level of the throw. Maybe it is thrown, okay, to the floor from this level. It can bounce back and then get to the same level of the throw. Once it is coming to the same level, then it means that the kinetic energy of the tennis ball before, the kinetic energy before is equal to the kinetic energy after the rebound. Okay. The same way that the snooker ball, when a force is applied on the snooker ball hits one ball and then rebounces. Okay, the level of rebouncing is almost the same. So they all indicate the fact that kinetic energy or velocity before is equal to velocity after. Please, are you okay? Janice, Immaculate, and Epia.
Yes, please.
All right. Then another characteristics of elastic collision is that bodies, the colliding bodies separate, they separate. Colliding bodies bodies separate after collision. After collision, the colliding body separates. So when the soccer ball or football is kicked with the leg is somewhere, the ball is somewhere. When the one snooker ball hits the other, the two bodies separate and go at their separate directions. Tennis ball, the same thing. So in elastic collision, the colliding bodies separate after collision. Once they separate, you could also see that there is no deformation of the colliding bodies. So these are the main features of perfectly elastic collision. Any question? No question. Any question?
No, please.
Okay. Mathematically, how do you express perfectly elastic collision? I earlier said that momentum and kinetic energy are conserved. So if you are writing a mathematical expression for a perfectly elastic collision, you have to write an equation for conservation of momentum and write an equation for conservation of kinetic energy. So I have two masses, M1. This has a velocity U1. The two masses are moving in the same direction. So M2 with the velocity U2. Now for such collision to take place, the one behind must move at a speed greater than the speed of this one. So it's like two cars in the same direction. Before they can hit, the one behind must have a greater speed to catch up with the other one in front. And when that happens, they can collide. And when such collisions take place, okay, the mass one exerts a force on the mass two. Okay, so mass 2 will be pushed forward because of the force exerted by M1. And Newton's third law, mass 2 would also exert the same reversal force on M1. So you realize that the speed of M2 would increase, whereas the speed of M1 would decrease. Please, are you okay? Immaculate, Janice, and Equia.
Yes, please.
Okay, so in effect, the velocity after collision will certainly be different from velocity before. And so if equation for conservation of momentum become M1 times U1. This is the momentum of the mass one plus M2 U2 being equal to M1 times V1 plus M2 times V2. This is the equation for conservation of momentum. Okay. And since kinetic energy is also conserved, let's write an equation for conservation of kinetic energy. Kinetic energy is half mv squared. So half m1 u1 squared plus half m2 u2 squared is equal to half m1 v1 squared plus half m2 v2 squared. So if a collision is said to be perfectly elastic, these are the two equations that can be used to solve a problem relating that. Okay. Janice, you see we can multiply through by 2 to eliminate the fraction. So please, I'm coming. Kenneth. 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 Okay, so we can multiply through by 2 to eliminate m1 u1 squared plus m2 u2 squared equal to m1 v1 squared plus m2 v2 squared. So if you are given a question and the collision is perfectly elastic, one way of solving it is writing a conservation equation for momentum and for kinetic energy and solving the two equations simultaneously. So let's solve a question. I'll later teach you another simple method of going about this. But for the meantime, let's use this method. Okay.
Okay, Mr. Dear. Mr. Dear, please, I have a question.
Okay.
Please, the conservation of momentum, is it only for bodies moving in the same
It
direction?
can be opposite. Okay, so that reminds, let me write it for when they are, let me write the equation for when they are moving in opposite directions. So in this case, we can have M1 from due east with velocity this. And we can also have M2 moving oppositely to M1 with a velocity U2. Okay, so to write the equation for conservation of momentum and kinetic energy, M1 times U1 minus M2 times U2. And this is on the assumption that momentum of 1 is greater than the momentum of 2. If it is the other way around, then M2 will be written first and then subtract M1 from it. So here I'm assuming that momentum of 1 is greater than momentum of 2. Janice and Akwi, are you okay?
Yes, please. So, can you use the momentum conserved in opposite direction to like derive?
I'm coming. Hello. The class is ongoing. I said the class is ongoing and you haven't joined. Okay, okay, thank you more maybe. No. I'll come again with a question.
So they are using the conservation of momentum in the same direction to derive a certain equation. And I'm asking, can you use conservation of momentum in like bodies in opposite direction
I can
to
use the
derive the
same
same
thing.
equation?
I can use the same equation, okay, for in one direction. But if I'm using it for the opposite direction, then I have to change the direction of the other one. You are talking about the coefficient of restitution formula, isn't it?
Yes, please.
So I can use the same formula, but in using it, I'll change the direction of what u, the other u. Okay. Or you can also use the same equation to also derive it though. But after you've used the two bodies in one direction, you don't have to use a different equation. You can still use the other one and change the direction. Okay. All right. So if they are, Janice, if they are moving oppositely, this is it. And this will be equal to M1 V1 plus M2 V2. Over here, you see, before collision, we can determine the directions of them. But until collision has actually taken place and visually, you have seen the directions of the M1 and M2 after collision, you cannot predict the values of V1 and V2. Or in questions, you can only determine the direction of mass 1 and mass 2 after getting V1 and V2. That is the reason for which I haven't shown a minus here, because I'm not sure. This is a formula. So if in real questions, after getting V1, V2, then you can determine the direction of this M1 and M2 after the collision. Janice, are you fine? Clear?
Yes, please.
Okay. So let's solve. I earlier sent the question on the platform, but let me resend it for maybe Janice. And here we are looking at question 1. Question 3B. Oh, no. Okay. 3A rather. 3A. Please wait for me to clean the board. Hey, I never knew my first marker is a permanent marker. Nice. Kenneth, mute yourself. Oh, are you Joe? Okay. It has to be given enough alcohol to go. Okay, so let's go through the question. We'll use the normal equation. Then when we finish, we apply the other equation. A tennis ball of mass M1 equals 0.04 kilogram. So we have M1 Kenneth, the question is on the platform. M1 equals 0.04 kilogram, moving with a speed of 5 meters per second. So its initial speed is 5 meters per second. Has an elastic head-on collision. Has an elastic head-on collision with a target ball of mass M2 equal of mass M2 equal to 0.06 kg. That was moving at a speed of 3 meters per second. 3 meters per second. Now, what is the speed? So what is the velocity of each ball after the collision if the two balls are moving A in the same direction and B in opposite direction? So what it means is that the word head-on as used earlier is even not correct, because for head-on collision, the two bodies must be coming from opposite direction. So it shouldn't have been used, but rather find the final velocities when they are moving in the same direction and when they are moving in the opposite direction. Please, are you with me? Are you?
Yes, sir.
Okay, so we are to find their final velocities when they are moving in the same direction and in it. So let's write the equation for same direction. M1 solution. M1 U1 plus M2 U2 must be equal to M1 V1 plus M2 V2. So we write it for conservation of momentum and write it for conservation of kinetic energy. So 0.04 times 5 plus 0.06 times 3 is equal to, there's no change in the mass. So still 0.04 V1 plus 0.06 V2. All right. So this is 4 on 100. Okay. So 20 over 100, 0.2 plus 6 on 100. So 1.8 is equal to 0.04 V1 plus 0.06 V2. Of course, because 2 is common, okay, let's sum this up. This is giving us 2. 2 is equal to 0.04 V1 plus 0.06 V2. Of course, we can reduce the values by dividing 2 by 2. 1 equals 0.02 V1.
Sir,
Hello?
sir, please, 0.06 times 3 is 0.18.
No, this is 6 over 100. So I have 18 over 100.
Yes, sir.
1, so 0.18. Sorry, 0.18. Thank you. So 0.18. Thank you. Okay, so let's add. When you add, this is what?
0.38.
0.38.
38.
Let's divide through by 2. Let's divide through by 2. Quick one. 0. Oh, Kenneth, Ekwe and Co. Divide through by 2.
0.19.
Ekwe, don't be quiet there. Janice, don't be quiet. Let's all be part of them. So this is equation 1. Equation for conservation of momentum. Then conservation of kinetic energy, instead of half, right? Let's use this. M1 times, let's do it straight away. 0.04 times U1 squared. So 25 plus 0.06 times 9. Okay. This is equal to 0.04 V1 plus V1 squared plus 0.06 V2 squared. Multiply everything and then give me the final value.
Sir,
Mm-hmm.
please, on the left-hand side, we have 1.54.
So 1.54 is equal to, so let's divide through by 2. When you divide 1.54 by 2, this is equal to
0.77.
So this is equation 2. So you solve equation 1 and equation 2 simultaneously. Okay. So let's bring equation 1. This is 1. You solve these two simultaneously. How would you solve it? How would you solve this equation? The best you can do is that make either V1 or V2 the subject and substitute into this. So if we make V1 the subject, we have 0.19 minus 0.03 V2 divided by 0.02. This is equal to V1. Please, is that okay?
Yes, sir.
Then, Epi, are you there? Janice,
Yes,
are you
please.
there? And you don't give me
Yes,
any
please.
feedback. Hey, as if I'm teaching Kenneth only. So you substitute this into the quadratic equation formula. 0.77 is equal to 0.02 times, this is V. This is V. 0.19. Okay, so let me teach you to simplify something. Let's do it. Let's do this. Let's divide each of this by 0.02 so that it will reduce. So V1 will be equal to divide 0.19 by 0.02. Divide this by that. What is 0.19 divided by 0.02?
0.095.
0.095 minus, divide 0.03 by 0.02.
1.5.
This is 1.5. So it will make it a bit linear. Else, when you leave it this way and your math isn't good, you can easily get it wrong. So 0.77 is equal to 0.02 You substitute whatever you have for this. Squared. Oh, sure. We omitted the V2. Okay. Plus 0.03 V2 squared. Then you expand. So it's like you are putting equation 1 into equation 2. Okay. Let's then expand. But the other way is that, you see, we can divide through by 0.02 so that it would prevent us from that expansion. So let's divide through by 0.02. 0.77 divided by 2. Quick one.
Sir, please 0.385.
Mr. Dear, please 0.
So we have 0. So plus plus
1.5.
0.03 divided by 0.02. 0.03 divided by this, so check.
Sir, please 0.77 divided by 0.02 is 38.5.
I said we are dividing through by this to eliminate this. So you divide this, each side of the equation by 0.02. So when you are doing this, meaning this is wrong.
Yes, please.
Open your eyes. I said you two, the rest of you must also be watching. If something
Mr. Dear,
goes wrong, please what?
please 0.19 divided by 0.02 is 9.5.
So we are dividing. Listen, we earlier substituted V1. And V1, we broke it down and we got 0.095. So we have substituted V1 into this equation, which is this. Okay. Now, because this is multiplying, we can reduce the value by dividing each part by 0.02. 0.02. 0.02. That's what I asked you to do. So what is 0.77 divided by 0.02?
38.5.
What?
38.5.
So 38.5 is equal to, you see, this will be eliminated. So we have 0.095 minus 1.5 V2 all squared plus 0.03 divided by 0.02.
1.5.
So 1.5 V2 squared. Is that okay? And it makes, when you do this, it makes your work simpler than combining everything and working. If you combine, the chances that, okay, if you are not careful, you may easily get it wrong. That's what I want you to learn. So now we only have what is within the bracket to expand. So we square 0.095. What is 0.95 squared? Zero point zero nine five squared.
9.025 times 10 to the power negative 3.
9.025 times what?
10 raised to the power negative 3.
Negative
3.
minus, then 2 times, multiply this by this, and multiply the result by 2. So 0.095 times 1.5. When you finish, you multiply by 2. This is, look at this, mathematical, this is like this. When you have a minus b squared, all squared to expand, you square this, a squared, you square negative b, which is plus b squared, then multiply this by this, and multiply the result by 2, minus 2ab. So that's what we are applying here. We are squaring this, then this times this, whatever we get, times the power 2. So take your time and do it for me. Kenneth, are you there?
Yes, sir.
Open your eyes and do it. Let's get it right.
Sir, please 0.285.
0.285 V2. Agree, I confirm. I do I confirm. Then
Yes.
plus, what
Yes,
is 1.5 squared?
It's 2.2.
2.25
25.
V2 squared. We can only square this, but this will still be the same. So 2.25 V2 squared plus, this is already there, 1.5 V2 squared. Okay, so let's add the like terms. Let's add the like terms. This is 38.5. Okay, we can only add this and this. So 2.25 plus 1.5. Then, okay, this is positive. So, okay. Then we will let this cross the equal sign. So we have 0.009025. I just want to express this in decimal. So 1, 2, 3. Yes. Okay. This is minus 38.5. Okay. Minus 0.285 V2 plus 2.25 plus 1.5.
3.75.
What?
3.75.
3.75 V2 squared. Okay. Okay, subtract this. Subtract 38.5 from this. 0.009025 minus 38. Straight away, we have a quadratic equation. So we have 3.75 V2 squared then minus 0.285 V2. Of course, this will give you a minus when you subtract 38.5 from this. So minus what? Minus what?
Minus 38.490975.
38.49
0975.
0975 is equal to 0. So this is similar to a quadratic equation, ax squared plus bx plus c is equal to 0. A is equal to 3.75. B is equal to negative 0.285. And C is equal to negative 38.49. Let's shorten it. 491. So it's obvious we have to use almighty equation. X is equal to negative b plus or minus the square root of b squared minus 4ac over 2a to find. Look at how lengthy this is. But we'll go through so that when we use the coefficient of restitution formula, you appreciate it. So our x here is equal to V2. Is equal to, substitute your figures. Negative and b is negative, so positive. 0. Janice, are you there?
Yes, please.
0.285. I'm sure you understand why it's positive. Because in the formula, we have negative here and b is negative. So it's like negative times negative. Plus or minus. This is b squared. So when you square a negative, it's positive. So just 0.285 squared minus 4 times A. A is 3.75. 3.75 times C. C is negative. So negative, negative. So plus 38.491. All divided by 2 times A. That is how to apply the almighty formula. So what is left is calculations. So do it. Put together what is in the bracket for me. Multiply, what is 0.2? Can you use your calculator to just give me what is within the brackets? Under the square root sign. And please, let's have somebody also doing it so that if something goes wrong, we can see. 0.285 squared. Kenneth, mute yourself. We are getting a mute it whenever you are ready to speak, then you come in. So somebody should also be doing it so that our answers will be the same. You are looking at what is under the bracket. 0.285 squared plus 4 times 3.75 times 38.491. What did you get?
24.030110.8.
Again?
24.030110.8.
Take your time. 24.030.
030 1108.
1108. Is that for everything? Is that for everything?
Yes, please.
And let's have somebody to say, recheck for us. Yes. Ajua, Equia, Kenneth, Immaculate.
Yeah, please, I got the same answer.
Yeah, that's what I want. So divided by, what is 3.75 by 2?
7.5.
So let's take the square root of what is under the brackets sign. What's the square root of 24.05? I guess this will be 4 point something.
$4.902.
So 0.285 plus the 4 points.
90205.
902. Okay, let's leave it in 3dp. Divided by 7.5. So we'll have two answers. 0.285 plus 4.902 divided by 7.5. So check this for me. And 0.285 minus 4.902 over 7.5. These are the two possible answers we can get for V2. So give me the first one, and somebody should also work on the second one. We are only adding the numerator and dividing by the denominator. What did you get for the first one?
$0.6916.
I mean, 0.6916. Okay, so this is meter per second. And what's the second one? What did you get for the second one? Immaculate and Co. Check, do the work for me. Don't leave it for one person.
Negative 0.6156.
Come again.
Negative 0.6156.
0.6.
6156.
So these are the two possible values of V2. And you use this to find V1. Don't forget we got the equation V1 is equal to 0.095 minus 1.5 V2. So once you have V2, use it to find the two possible values for V1. Kenneth, are you there?
Yes, sir.
So do it. You do it. We are looking for, we have the two answers for V2. Do it for 0.6916. And then, Ekwe, are you there?
Yes, please.
You will do it for negative 0.6156. The rest of you must also do it so that, because we shall confirm their values. If they had, you also got the same thing. So do it for, so that we could get the other two answers for V1. Then mute yourself. When you are ready, you speak.
Ezekiel, please. V1 is equal to
V1 is equal to
0.47.
So which one did you, is it the first one, first of V2 or the second one?
The second one.
The negative value.
Yes, please.
Okay, so he said what? What's the value?
$1.0184.
1.0184 meter per second. And then what's the other value of? Okay, Kenneth, are you ready with your value? Please, those of you who are also rechecking, did you get the same thing?
Yes, please.
Okay. Kenneth,
Yes, sir.
your answer.
For the first V2, I got 1.0244.
1.0244. Those of you who rechecked, do we have the same answer? The confirmation people, do you have the same answer for the first value of V2? Then you are not doing it.
Yes.
What? Hello?
Yes, please.
Akuya, did you get the same answer?
Yes, please.
Okay. So these are the values of V1 and V2. You see how lengthy this is? Okay. So let's also look at using the coefficient of restitution formula. Take note of the answers because we are going to use that to see if we can get the same value. So take note, okay? And you see how, if you are not careful, that your chances of getting this wrong very, very, very high. And this is even for when they are moving in the same direction. Adwa, go ahead.
Teacher, please, I have negative 0.942.
For which one?
For the 0.6916.
Okay, then let's confirm. Let's confirm once there is a different view. V1 is equal to 0.095 minus 1.5 V2. So if I substitute the first value of V2, yes, 0.095 minus 1.5 times 0.6916. Yes, I think you have negative. Multiply 1.5 by 0.695. Yes, what did you get? 1.5 by 0.6916.
1.03.
1.0365.
365.
So subtract this from 0.095. What did you get?
Minus
Meaning you didn't do a perfect job. Minus what?
0.9.
9. 8. Minus 0.9.
415.
Can it?
Yes, sir. Yes, sir.
When you are working, open your eyes and take your time. Immaculate or Sheho Dinya is only class. And no. You want to say cage in your fees. So that's it. Now, a quick introduction to the method of, and look at it. This is even for when they are moving in the same direction. When the two masses are moving in the same direction, you now would have to do it for when they are moving in opposite direction. What a great deal of work. So let me introduce you to the coefficient of restitution. So, Yanis, are you there? Yanis is gone. So this is equal to M1 V1 plus M2 V2. Group the ones. M1 U1 minus M1 V1 is equal to M2 V2 minus M2 U2. Factorize out the common term. Is equal to M2 out, V2 in minus U2 in. That's maybe equation 1 because we haven't, okay. But yeah, because this is equation 1, this is 2. Then write it for conservation of kinetic energy. We had M1 U1 squared plus M2 U2 squared is equal to M1 V1 squared plus M2 V2 squared. And here, don't forget, you are considering the bodies moving in the same direction. So group the ones, M1 U1 squared minus M2 M1 V1 squared is equal to M2 V2 squared minus M2 U2 squared. M1 out, U1 squared minus V1 squared in, M2 out, V2 squared minus U2 squared in. And this is equation 3. Now divide equation 3 by equation 2. When you divide, it's like left-hand side divided by left-hand side, right-hand side divided by another right-hand side. So this will be divided by M1 U1 minus V1 is equal to M2 V2 squared minus also divided by the right-hand side of this. So this and this will cancel. The numerator is difference of 2 squared. So U1 minus V1 times U1 plus V1, all divided by U1 minus V1. So this and this will cancel. The right-hand side, the same thing. V2 minus U2 times V2 plus U2, all divided by. So we have this and this also canceling out. In effect, this is what you have. U1 plus V1 is equal to V2 plus U2. Group all the U's and then V's. So U1 minus U2 equals V2 minus V1. You can even use this without the coefficient of restitution thing. You have U1. U1 was given to us as, I think, 5. U1 has a velocity, 5 meters per second. So this is 5. What is U2? What is U2 given to us?
3 meters per second.
So minus 3. Because they are moving in the same direction. Don't forget, we use the equation of them moving in the same direction to do this. So this is equal to V2 minus V1. So straight away, V2 would be equal to 2 plus V1. Okay. Now, let's clean the other side. Then, okay, I can even use this. Pick either equation 1 for conservation of momentum or equation 2 for conservation of kinetic energy. Here, you are free to choose any of them. If I choose conservation of momentum, M1, what is M1? Is it 0.5?
0.04.
0.05 times U1. U1 is 5. Plus, what is M2? What is M2?
M1 is 0.04.
0.04.
Yes.
plus M2. Is it 0.06
Yes.
Yes, sir.
times what's the velocity? 3 is equal to 0.04 times V1 plus 0.06 times V2. We've had expression for V2. So wherever you see V2, substitute. Please sum this up for me. 0.04 plus 0.04 times 5 plus 0.06 times 3. I think we got it. So if you have it, tell me.
0.38.
0.38. Good. It's equal to 0.04 times V1 plus 0.06 times, this is V2. V2 is 2 plus V1. So let's expand. Oh, we can even divide through by 0.0. Okay, let's expand. 0.04 V1 plus, I guess this is it 0.2? 0.12, 0.06 times 2.
0.12.
So 0.12 plus 0.06 V1. Group like terms. So we have 0.38 minus 0.12 is equal to, add 0.04 to 0.0. I get the 0.10. 1 is it 0.10?
0.1.
V1. Therefore, subtract this from this. When you finish, divide by that. 0.38 minus 0.12. Oh, hurry up. 0.38 minus 0.12 divided by 0.1.
2.6.
That is 2.6 meter per second for V1. None of the V1 values has this. So you do it again. But this is the correct. You see your V1 values you had. None of it has this. Even the first one was wrong. Adjoa, what is the V1 value? What is the V1 value we got when you use this?
It's negative 0.9424.
Meaning something went wrong. You do it again yourself. Okay, so once you have V1, you can easily find V2 using this equation. V2 would be equal to 2 plus V1, which is 4.6 meter per second. It means in our calculation, using the almighty form, something went wrong and perhaps we didn't see. But these are the answers. V1 is 2.6 meter per second. And you see, they are all positives. They are all positive, meaning that after collision, both bodies were still in one direction. Please, is that okay?
Yes, please.
But you will still use the almighty formula to confirm. Let's confirm the answer. It's an assignment for you, for all of you. We can't get that wrong. So, in fact, when you use the coefficient of restitution method, okay, U1 minus U2 is relative velocity of approach. Then V2 minus V1, relative velocity of separation. Okay. Okay, let me, because some of you were not with us, let me use the time to explain. And don't forget, these are for one, when they are moving in the same direction. When they are moving in the opposite direction, you negate one of them. You see the momentum of, which one has a larger momentum? Is it M1 or M2? 0.04 times 5. What is it? This is 0.2, I guess. And then this is
Yes, please.
0.118. So this one has a greater momentum than this one. So you negate the velocity of M2 when they are moving in opposite direction. So, so here you aren't going to derive another equation. All that you do is that for opposite direction, you negate U2. You are negating U2 because at the end of it, it will give you a lesser momentum than M1, U1. So you have using U1 minus U2 is equal to V2 minus V1. Okay. U1 minus U2. And this is simply to mean that this one is in opposite direction, the velocity. So we have U1 plus U2 equal to V2 minus V1. So 5 plus 3 to be equal to V2 minus V1. Therefore, V2 is equal to 8 plus V1. Then you use any of the equation, either momentum in the momentum equation. Don't forget, we have also taken account of the opposite direction. The reason for which we have negated that. And so you go through it as you've done. 0.04 times 5 minus 0.06 times 3 is equal to the same thing. Then when you finish, you substitute V2. 0.2 minus 0.18 is equal to, you substitute V2, so 0.04 V1 plus 0.06. Now V2 is 8 plus V1. you close the brackets. Go through it and find whatever you are looking for. Even this is it. So I'll divide through by 2. So this will be 0.01 is equal to 0.02 V1 plus 0.038 plus V1. Okay. What is this is 24 divided by 100. So 0.24 plus 0.03 V1. Help me find V1. This is 0.01 minus 0.24 is equal to 0.05 V1. Therefore, V1 will be equal to, and subtract 0.24 from 0.01. Subtract 0.24 from 0.01.
So zero,
Negative
Negative
0.23.
0.23. This divided by 0.05. And this is equal to negative what? Negative what?
Negative 4.6.
Negative 4.6
negative 4.6.
meter per second. And you use this to find the other one. V2 will certainly be equal to 8. This is plus V1, and V1 is negative, so minus 4.6, which is 5. Hey, it will be 4. 4 point what?
Three.
Eh?
3.4.
3. 3.4
Yes, sir. 0.4.
meter per second. What it means is that when they are moving oppositely, after collision, one mass will point to the positive side, okay? V2, the M2 would have a velocity which is going this way, and the other one will go the opposite way. That is how come this is negative. Okay. Are we okay? Janice,
Mr. Yeah.
are you okay?
Yes, please.
It's it's not so difficult, but you need to understand and go to. And you see, the coefficient of restitution formula is very, very simple to use. When you use relative velocity of approach is equal to the relative velocity of separation. Very, very simple to find V1 and V2. But I will still want you to use the simultaneous equation to confirm our answers. I haven't. You will do it and send it to me. I'll also confirm it tonight by doing it. Okay. Can I clean the board? Can I clean the board?
Yes.
Yes, sir.
let me talk about the coefficient of restitution thing for, I think, Janice, who wasn't with us. So when we went through the whole thing, we concluded that velocity of approach u1 minus u2 is equal to v2, the relative velocity of separation. And Janice, this side, the left-hand side is what we call as, when we talk about relative velocity of VA and VB, we are comparing the velocity of A with respect to B, or comparing the velocity of B with respect to A. So the relative velocity of A with respect to B is equal to V of A minus V of B. Relative velocity of B with respect to A is also V of B minus V of A. So whenever you have one velocity subtracted from another, we can call it as the relative velocity between two velocities, okay? So we call the left-hand side as relative velocity of approach. As the two bodies approach, these are their velocities. So relative velocity of approach. And this is also relative velocity of B of 2 with respect to 1. This is 1 with respect to 2. This is 2. And since these are final velocities, we are calling this as the relative velocity of separation. When they separate, they are final velocities. So that's the name given to this side. Now, if you take a ratio of relative velocity of separation over relative velocity of approach. This ratio is what we call as the coefficient of restitution, represented by the symbol E. So the coefficient of restitution is just the ratio of relative velocity of separation to the relative velocity of approach. So we say E is equal to V2 minus V1 over U1 minus U2. You may see it differently in other books. And this is how other books also represent the same thing. You see, we have what U1 minus U2 is equal to V2 minus V1. Other books, representation is that they will want the order to follow 1, 2, and not 2, 1. So what they do is that when you factorize out negative, you have V1 coming first, minus, to get positive V2, this must be minus V2. So that when you divide V1 minus V2 on U1 minus U2, you have a negative 1. And this ratio is what we call as E. So it is either you want it this way. Vero, give me a second. I'm coming. A minute or two, please. So it can be this. Okay. Sometimes what we do is that instead of the negative affect the E. So we have V1 minus A, blah, 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 is equal to negative E, or we equate E to -1. Whether you are presenting it this way or this way, the value is the same. Okay. Please, is that okay? Hey, human beings or
Yes, please.
now the use. Let's look at the uses of the coefficient of restitution. What do we use it for? You see, when we were going through the theory on the types of collision, we said that, or we saw that for perfectly elastic collision, the value of the coefficient of restitution is equal to 1. Okay. And for perfectly inelastic collision, the value of the coefficient of restitution is equal to 0. So we use this concept of coefficient of restitution to determine whether a collision is perfectly elastic or perfectly inelastic. So it is used to determine whether a collision is perfectly elastic or perfectly inelastic. So if, look at it, we saw that for perfectly inelastic collision, E is equal to 0. Then the two bodies after collision move with a common velocity. They collide or they combine, forming a composite body and move with a common velocity, meaning V1 is equal to V2. Final velocity of 1 is equal to the final velocity of 2. You can see it here. E is equal to V2 minus V1 over U1 minus U2. Now, if E is 0, you have only V2 minus V1. 0 will be equal to V2 because once this is 0, when you multiply 0, and you have V2 equal to V1. Confirming it. If it is this one that you want to use, then once this is 0, we'll get the same thing. Please, is that okay? Class, is that okay?
So the V1 is for elastic, inelastic.
Pardon?
V2 is equal to V1. Is it for
It's
elastic or inelastic?
perfectly inelastic. I said for perfectly inelastic collision, after the collision, the two bodies combine and move with a common velocity. We'll come to the equation. We've done it extensively for elastic collision. We'll talk about inelastic later in our meeting. Okay. So this is used to determine the coefficient of restitution is used to determine whether a collision is perfectly elastic or perfectly inelastic. The other second use is that it is used to determine final velocities of colliding bodies. Kenneth, are you there? Ado, are you there? Janice? Hey,
Yes.
they are gone. So the second use of the coefficient of restitution is that it is used to determine the final velocities of colliding bodies. Yes. And that's what we've just used. We use that to determine V1 and V2 easily. Look at the ordeal we went through when we were using the simultaneous equation involving one linear and one quadratic, and we couldn't even get it. But when you use a coefficient of restitution method, you get it easily. Okay. So
Yes, please.
this is the whole history of perfectly elastic collision. We'll talk about, okay, we have about 5 minutes or 9. So let me talk about inelastic. Or Yakuya, you have a question? Or Adwa or Kenneth or Janice?
No, sir.
Okay. So for perfectly inelastic collision, this is the equation. Yes, momentum is conserved, M1, U1, whether they are moving in the same direction or if they are moving in the same direction, plus M2, U2. But what happens is that after collision, the bodies combine. M1 plus M2, and they move with a common velocity. So the final velocities of 1 and 2 is the same. Over here, kinetic energy is not conserved. So K initial is not equal to K final. Either the initial is greater than the final, or the final is greater than the initial. Or K kinetic energy initial is equal to K final plus sound energy or heat. So part of the initial kinetic energy is converted to other forms of energy. And so the final is always less than the initial, or the initial is less than the final, depending on the kind of system we have. So this is the equation for perfectly inelastic collision. All right.
Okay, sir.
All right. So, if you have any question, Janice, if you have any question, ask. If you don't have any, your homework is to use the equation to confirm whatever we got when we use the coefficient of restitution. Go through it, check what went wrong. I'll also do same. Okay. So good night to all of you. Okay.
Yeah.
Yeah.
Please, so the final velocity in elastic collision is not the same of colliding bodies.
Of elastic, kinetic energy is conserved in elastic, but it is not conserved in inelastic. So
So
which
the
one are you?
final velocities in elastic of the colliding bodies, are they the same?
Are almost the same. The thing is that, you see, we can't have a perfectly elastic or inelastic collision. Okay. And this is when you strike a tennis ball to the ground. Yes, after the impact, it will bounce to the level of your hand. But you could still hear sound, meaning that part of the energy, kinetic energy, is also converted to sound energy. But we assume that the loss is very, very, very small. That is why I said we cannot have a perfectly elastic and then perfectly inelastic. But in these examples, as I've said, we almost round it that kinetic energy is conserved, right?
Okay.
All right. All right. So bye-bye to all of you.